of the major electric transmission system operator in Europe, actually managing the transmission grid in the Netherlands and in parts of Germany. Welcome, team. Welcome. Thank you for accepting our invitation. I see that we have already about more than 40 participants to this online talk, and others are coming. I will just introduce you the structure of this talk. Maybe not all of you are aware of how Zoom works and how we organize FSR talks. We will have 45 minutes. We will discuss, me and Tim, in the first part. We will address this topic on to be in the shoes of an electricity TSO, and then towards the end we will have a moment to interact directly with you, the audience. And so during the entire talk, you feel free to write down questions that you want to address to Tim and to me. As you see in the bottom of the screen, you should have a Q&A icon. If you click it, you have a window and you can write down your question there. And of course, in the meanwhile, you can also chat among yourselves in the chat box. So questions for Tim and me in the Q&A chat, and chat among you participants, or general comments in the chat session. Perfect. So let's start immediately to address the topic. Probably most of you know that transmission system operator play a fundamental role in the. I will also share my screen, so because we prepared a slide to the beginning to introduce the topic. As you know, electricity TSO play a fundamental role in the electricity system. They perform different tasks. They operate the electricity grid, the transmission grid, with the aim to ensure the continuous and secure flow of energy in the system. They plan, build, and maintain the physical infrastructure. In short, they ensure the physical layer upon which electricity markets run. And since they deal with this physical layer, in their activities, they are constrained. They have to respect some technicalities, and not all the people that deal with electricity issues are completely aware of these technicalities, of these technical aspects that are extremely important. That's why we invited Tim, because I know that TenneT, but Tim will confirm, has recently developed a tool, a software that can be used as a pedagogic tool for understanding these issues. So welcome, Tim. Why did, maybe my first question is, TenneT develop this tool that we are going to see in a minute?
Yeah, hello. Thank you very much for this invitation and this opportunity to talk to you. And yeah, I had one experience 2 years ago that in a big workshop, a professor for energy economics stood up and asked a question. I'm hearing that sometimes TSOs are only using 60% of the capacity of their lines, of one single line for production, and that 40% are not used. And I completely don't understand why they waste these capacities. And this was this special example, but also during the entire negotiations of the clean energy package, it was not really understandable for somebody who has not studied electrophysics why there are physical limits in the electrical grid and what happens if you ignore the physical limits. And therefore we decided we want to make it possible within 6 minutes to become an operator of a high voltage grid yourself. And so with this software, you can try it out yourself and can make the experience how it is to run a high voltage grid.
So maybe we can see this tool and start to discuss some of the things that we can learn from it directly with you. I see that you are starting to share your screen and that's actually the interface available on the ENSOE website.
Exactly.
So can you explain what are we seeing? What is on the map?
Yes. So we see a super simplified map now, a super simplified grid covering, let's say, Germany and the Netherlands and Belgium. And it's, of course, it's simplified. We have also more complicated grid models, but we always start with this easy one. And you see the blue balls are generation capacities and the orange boxes are consumption capacities. At the top left, you see the frequency indicator, and at the lines, you see a value in percentage, and that shows how much of the physical capacity, the thermal capacity, is used in this very moment. And as in this very moment, the consumption and generation at each node is equal, there are, of course, no loads running in the lines, and therefore the value is always zero. But, and that is the nice thing with this model, you can really change the value of every consumption or generation capacity. And now we say it's, let's say it's Monday morning, 7 o'clock. The Dutch people are waking up and are making coffee and starting their factories in the south of the Netherlands. And then you can see already with this small change that power starts to flow, frequency is going down, and we do the same with, let's say, half an hour later, also the Germans wake up. And
they sleep a bit more.
Yes, yeah. And also now BMW Motorworks in Munich is starting up its production. And so what you see now, power is flowing on this line, and it really this model is really working with physical laws. So you have input parameters, the capacity of each line, the resistance, and then the model calculates in real time the electrical flows on each line. And and what you also see now, the demand is bigger, 6,000 megawatts bigger than the generation, and therefore frequency is going down really dangerously. And but in this moment, the problems would be solved by the market, because if you use so much power, you are obliged, or your electricity supply is provided to buy the same amount of power in the same moment. And so let's say the supplier for the electricity customers in the south of the Netherlands buys the power at a cheap power plant in the Netherlands, and the same does the supplier of BMW. He buys also the power at a cheap, reachable generation, and let's say it's done by coal power in the north of Germany. And so now the frequency is back, and you could say everything is in order, values don't look too high, and everything seems to be perfect. And
yeah, because the system is balanced, the same injections and withdrawal are equalized, so the alternate current continue to alternate at a stable frequency over the line. All the thermal limits of each line is respected. There is no red circle, right? No, yeah. So everything seems functioning well, right? Yeah. At least this is what you could see from this map at the moment.
And this is this nice thing about this model. We are now something like 3 or 4 minutes in this presentation. And now you can ask with this model your audience, for example, looking at the left connection, which is used to 66% of its thermal capacity. And now the participants, they in this video conference, they can't answer verbally. But the question is to everybody, what would you say? What would you say? Is 66% a sign that there is really 33% can be used, 34% can be used additionally, and that perhaps the TSOs are a little bit lazy perhaps, and they leave their unused capacity? Would you say it's 66%, it's in the middle, it's medium, it's okay, seems to be reasonable? Or would you say that 66% is perhaps already a little bit too much? And maybe you type in now your answer in the, Nicolo, it's in the question and answer section that should be typed in, or in the chat?
Maybe in the chat is easier. So we,
yeah.
If the participants, but then we need to, yes, I invite all the participants to say, to write in the chat and see and tell us, do you think that this 66% usage rate of the internal line in the Netherlands is safe, or is it not? Safe or not? Yes or no? I see that 3 people already say perhaps it's too much. Ruud said yes, so probably he considers safe. Dirk said no. So there is a mixed view on this.
Yeah, and this is really, that is why we constructed this software. And what's so nice about you
because
can you
now
don't
we can see
you don't need to have any pre-training. You can simply try it out. And now we try it out, and it can always happen that a tree falls on a line, that a lightning strikes a power line, or that a helicopter flies in a line and suddenly a line switches off. And then in milliseconds, the power is looking for new ways to flow. And in this situation, you see the power is flowing back to Germany, and over Germany, then back to the customers in the south of the Netherlands. And you see here 188% of the line would now be used. And that is above the thermal capacity, way above. And then the automatic security protection, which also switches line off.
Because, and please tell me if I'm wrong, the thermal line indicates what is the maximum flow of energy that can exactly pass through this line. If it's too much, then the line becomes too hot. There is risk of fire, or maybe the line becomes longer and then it sag, and maybe it touches something closer to the ground, so create danger, risk for the people around it, right?
Exactly, and you explained it very well. And now you see, just 1 minute ago, we thought we are in a happy life, and everything looked so relaxed, but only one tree falling on one line has now caused a problem that is spreading all over Europe and would cause a blackout. And so let's go back to we switch on the lines again. But we see now that this situation is not safe in case that an accident happens. And so in contrast to a street system, we really have to make a traffic forecast that even if one accident happens, that should not lead to an over usage of another street. And so what we do for every hour of every day in the entire year, we do something like a perfect traffic forecast for every line. And here we see 66%, it has been shown it's too much. And we have to do redispatch. That means we have to use the line, the power plants in another way than the market outcome would say. We would simply increase the generation behind the bottleneck. And
in the south of Netherlands?
Exactly, and we would reduce the generation in the north of the Netherlands to avoid this possibly dangerous situation in the electrical grid. Now the situation is safe. If we now switch off this line, no red bubbles. And so that is our, and we have to do this test for every line, for every grid element, for every hour, in every possible situation, changing renewable, changing generation, changing consumption. So that is our daily job.
Great. So you try to forecast the use of the grid by the network users, by generation and consumption. You estimate what is the maximum capacity on the various lines that can be offered to the market for transportation of electricity. And in case some market outcome is dangerous, like for instance, the one we had before, because market parties were deciding to supply more consumption in south of Netherlands with more generation in the north of Netherlands, but you consider that market outcome not secure enough, then you intervene after the outcome of the market, the auctions in the market, by redispatching some of the power plants under the control of the TSO in order to ensure safety. This is what you do basically on the short term, right? From now to the next hour, or maybe from now to the next day. But of course, over the years, you can do also other things, right? You can expand the grid. Maybe we can see this on the power tool on the simulator.
Yeah, we can say that now we have, with the clean energy package, we have got an additional obligation to always make cross-border trades possible, and that will lead to more usage of the lines. And also here you can already see values that are really high. And then in the short term, we would also do redispatch. But in the long term, the strategy is, of course, to overcome the congestions. And what we would do is simply, and what we are already doing now, is to build lines. And here you see that we are building north-south connections in Germany. I can also switch on this one, and you can see that we are with additional lines, we can also overcome the congestion. And that is, of course, better, because then we don't have to do so much redispatch, but we can really transport the renewable power in that very moment when it is produced to the customers. And that is the most efficient way how to make use of renewable electricity.
Yes, because renewables actually create a new challenge for electric TSO. There is the deployment of significant amount of generation capacity over the past 10 to 15 years, and frequently not in the places where generation was used to be, but maybe in new places far away from load center, or maybe from existing lines. And then, of course, there is the problem of renewables having specific generation patterns. In particular, wind and sun follow the availability of the primary resource, or of the availability of the sun and the wind, and not necessarily respect, let's say, demand for electricity by final customer. Is it, Tim?
Exactly, and also this you can get an impression about this. Let's say it has been raining during the morning and there have been heavy clouds, but and now suddenly the clouds go away and the sun comes out, and suddenly the generation of solar power goes up, and also you can say let's say the North Sea countries to decide to build a lot of wind power in the North Sea, and so you see with the software you can simply easily build something and then switch it on and then see how this changes the power flows. And so you can really see with only the sun coming out and some offshore wind power plants going into generation, you see that the situation is now completely changed and the lines are now completely overused. And so what we would do, of course, we would switch off the fossil generation if everything, or the market would switch off the fossil generation if everything could be provided by solar power. And you see here what happens if you build offshore wind. You see that you don't only have to think about the offshore connection and how you bring the power to the shore. It's perhaps even more critical to also have a plan how you integrate the offshore electricity in the onshore grid, and to think about how you want to do it if you build an offshore wind park, and how this will change the usage of the grid. We are doing projections for, let's say, for entire years, for all possible market situations, a lot of solar power, little solar power, and that is then how we do grid planning, that we plan a grid that is efficiently taking up as much offshore power as possible. And so, and everything changes everything if you build new interconnectors, if you build offshore wind farms or so, then you also have to adapt the planning of your internal grids.
And interestingly, from the tool, you can see it easily. The negative implications sometimes of holding a generation or a consumption element in the system, these negative implications are not just in the neighborhood of such element, but sometimes are quite far away. For instance, by holding this wind production in the North Sea, we saw that there is a significant more usage of the line between north of Netherlands to Germany, but also from north of Germany to south of Germany. So sometimes the implications are not so obvious of a change in the pattern of production and consumption, and TSO have the challenge to try and anticipate them. Of course, TSO are not the only one to try to solve and to use to promote the efficient use of the resources, because market rules, the market design should induce as far as possible network users, so generators and consumers, to make the best use of the resources compatible with the limits in the grid. But of course, TSO are the ultimate that have to step in when there are sudden problems, and of course have to plan to improve the situation over time. Because if we see that there is the best energy to use are exactly offshore wind in the North Sea, and there is a very congested line that is connected to that, on the long term, the best thing to do is to expand such grid connection. Right, Tim?
And yeah, that is true. And what also in a few days, the Commission will present its sector integration strategy and its hydrogen strategy. And also with this model, you can also discuss this sector coupling topics, because you can see what how huge the difference would be whether you build new hydrogen electrolyzers, which will be simply huge new consumption. If you build it somewhere in the middle of the continent, then it is completely different as if you build it close to the offshore wind power plants. If you build it close to the offshore wind power plants, it will be fine. If you build it somewhere in the middle of the continent, then you see then, of course, the power would need to flow through the lines to this new electrolyzer somewhere in the middle of the continent. And that would increase the transport task for these lines, and that would probably make additional lines necessary. If we look that Germany wants to build 5 gigawatt until 2030, Netherlands 4 gigawatt, that are already amounts of capacity that are really significant. And if you really take a decision over the entire system cost by taking the decision where you build these new electrolyzers.
Thank you, Tim. I think that we can start looking at the several questions that the participants wrote in the chat. I see, for instance, that Christopher asked a very direct question. What would be an acceptable threshold for the power line? Probably wrote when we were dealing with the north or south Netherlands line. Do you have, you in a sense, the TSO, do they have a rule of thumb for understanding how much of a grid line is secure to use or not? What are the procedure that they use to estimate how much of a line is safe to use?
Estimate it. You can't estimate it because it's really depending on the grid situation, and you really have to check it out so that that you really do the test for every grid element. What happens if you switch it off in your simulation? And you can't do a rule of thumb. And it really, and perhaps you can even see it at this picture in the right side. So Germany, you have 3 or 4 parallel lines, and so if one of them drops, then it's not so critical as, let's say, as if a line drops in a situation in a location where you only have 1 line or only have 2 lines. So really super simple would be to say if you have 2 lines, you can use 50%. If you have 10 lines, you can use 90%. But it's by far not so easy, and you really have to calculate it. You can't do it by your gut feeling.
So actually, indeed, TSO developed this common grid model to try and estimate how much capacity is available on the system and to coordinate their actions among themselves. Okay, let's see another question. Via Paka ask, how does redispatch work in a market? Does the TSO purchase power from generators to ramp up supply in matters of minutes?
I would say we plan it several hours ahead.
So you reserve some, usually TSO reserves some capacity from some generators, and if problems arise, they order to this generator to produce or to stop producing.
That's a good question. I would not be sure to say we reserve power plants, but we have some special. There's a special power plant reserve in Germany. There we reserve something, but mainly we try to do redispatch with those power plants that have not been activated by the market. And so I would not say that redispatching is about reserving ahead, but simply using that power plants that have not been activated by the market.
Okay, and so of course the TSO, when already dispatch power generator, it incurs a cost, and then
Yes.
this cost enter the revenue, the allowed revenue of the TSO, and then is finally recovered by, I assume, network charges or the imbalances charges paid by market players that are not balanced, right?
Yeah, but let's say redispatch is even takes place if everybody is balanced. So it's
Yes.
we redispatch in a balanced grid, or we redispatch in a balanced market because we have congestions in the grid. And so it's if somebody is not balanced, then it's the fault of the market participants. And but even if every market participant balances his balancing group perfectly, we as grid operators see that okay, the grid can't transport what the market is asking for, and then we do redispatch.
Okay. Then a question by Philip. How likely are accidents on the transmission lines? How often does it happen that a line it's not usable, go trip off?
I would say this happens several times per year, and especially if you have certain situations like storms, extreme weather situations, and that are then likely incidents where, but also sometimes a helicopter flies into a power line and then also suddenly cut off. And if you look at the design of helicopters, they
Yes.
even have purpose-made cable cutters at the helicopters because somehow helicopters are used to fly into power lines. And so that also happens sometimes.
But then most of the time these accidents are managed properly, because in the end major outages, at least in the European on the European grid, are quite rare, isn't
Yeah,
it?
because we have done our traffic forecast well, and we have planned ahead for the case of an accident.
Great. Let's see. STSO, do you sometimes have to restrain renewable generation, or is it more the role of the DSO? So are TSO frequently curtailing renewable generation?
It happens. It happens from time to time. I think we in Germany we have the obligation to first of all reduce fossil generation as much as possible, and only if this doesn't lead to the results that we need for the grid, then we go to curtailing renewable production, but it happens.
Okay. And Joseph also asked, do you think that DSO distribution companies also do that more than you or not?
I don't know the distribution between TSOs and DSOs about curtailment, but what I know is that for Germany that we are now in a process that we are developing a comprehensive system and a comprehensive vision together with the DSOs, so that we can also do redispatch with smaller installations, that we can smoothly do redispatch also with installations that are under the control and in the grid of a DSO, so that the capacity of the total capacity of that we can reach with redispatch measures will increase soon. Now it will also that smaller power plants can be reduced or increased for redispatch purposes. That's just in the making.
Yeah, because now a significant amount of additional renewable generation is connected to the distribution lines, the coordination between TSO and DSO is actually a major topic.
Yeah.
Another question by Gemma. Maybe it's a tough question. Let's see if we are able to explain it, to answer it easily. Could you please explain how you calculate the 70% threshold established by the clean energy package? So you mentioned earlier that the new electricity regulation oblige TSO to offer a certain share of the capacity of a line to market transactions. How do you compute this quantity, this share?
I would say that is a super topic for, let's say, a 2-week course of the Florence School of Regulation. And
I can imagine.
And we should clearly go and plan for it. And it's really super complicated. And it's not so easy that if we, let's say, it's not so easy that we say here we have now on the border between Belgium and the Netherlands 75%, and that's it. That would be it's a simplification for explaining purposes. But in reality, it's about each grid element, also internal grid elements, not external grid elements. And then the capacity of each internal grid element has to be made available for cross-border flows, also respecting this security margins, this accident-proof margin, which we call as which the experts call N-1 criteria. But that is really, and we doubt that any politician who has adopted this regulation, and even sometimes we ask ourselves whether the experts in the bureaucracies who have prepared this decision really could explain how it is done. So really complicated.
So just to send a very clear message, the 70% is not simply the 70% of the nominal capacity of an individual line. There are exactly. So this is not, so it's not simply the number you saw in the tool. Actually, the calculation is more complicated and requires considering these security margins and the various flows internal to each network element. Okay, so maybe one other question, because we are running close to the end of our time. Julius posed a slightly different question. He asked, what do you consider is the biggest obstacle or the greatest challenge when building new lines to remove congestions in the electricity grids?
Acceptance. Whether local politicians support us or whether they don't support us. When they support us, then it's possible. When local politicians go with and demonstrate with the citizens against the project, a new infrastructure, then it becomes extremely difficult. And so it's acceptance. It's not technology. It is not getting the material. It is not financing. It's acceptance.
So I would say, yeah, it's something general nowadays in Europe, especially social acceptance towards or of new infrastructure. This is usually the problem. Okay, maybe the last question. Could you explain again, Gemma, but I'm not sure it's an easy question to answer in 1 minute. Could you please explain what happened when loop flows appear?
Yeah, that is not difficult to explain. A loop flow is simply a normal behavior of an electrical grid. Let's say we have a lot of production in the north of Germany and a lot of consumption in the south of Germany, then the electricity is not only flowing the direct line through Germany, but it's looking at all lines. The electricity is looking for all possibles how to reach its targets. And the electrons also don't go out and check whether there is a border sign or not. And so also that means the word of loop flows is also misleading, because in a meshed AC grid, the flows are using all lines, and they don't check whether there is an international border or not. It's simply, and a loop flow free operation would mean that you don't have any flows in a grid. So I would not call it a loop flow, I would call it a flow from the source of generation to consumption.
Okay, thank you. I think we have only a few minutes. I don't know if you want to tell us something else about the tool that Tenet and then NSOE developed. I know that there are other resources that people can explore some functionalities, right?
Yeah, very quickly. So first of all, the model is freely available for everybody on the grid, on the internet, both on the NSOE website and on the Tenet website. Secondly, you can build your own grid. So if you want to explain something for Italy, you only scroll down there and then you push here on this person, and then you are in expert mode, and then you can build your own grid. You can even save it and send it then by email to your colleagues, and you can and we also have, now there's even a Korean grid, and Japanese colleagues are working with it. Okay. Then we have prepared a little bit more complex grid models, just that you find that this, but this is still very simple. In reality, we are managing something, I think, like 12,000 grid elements. Here we are talking about 70 or so. So that is still super simple.
And it shows that basically without digital tools, you wouldn't be able to manage all of this.
Yes.
Really, it would be impossible for humans to do it.
And then last point, if you now have got some appetite to work with this tool, there is something like an explanation mode. If you go to this button play, then you get tasked and where you are really led through a storyline, and where you can learn how to operate the model. And that is really the best way how to get acquainted. Whenever you want to use it for something and you have questions, we from the Brussels office of Tenet are really happy to answer them, and don't hesitate to send us an email or to call us. And you can really tailor-make it for your communication purposes. And yeah, and on the Tenet website, if you the third storyline is really complicated, and if you accomplish it, then you get the link to the Tenet HR website with the job offers, and there you can then you are qualified to apply for a job. But that's of course a joke. Everybody can apply, but it's so we even use it also for job fairs. We use it for our new employees. We use it for everybody who has not studied electrophysics, and so you can also use it to discuss new grid projects. You can discuss an offshore energy system with it. Whatever you want is becomes really easy to understand and to communicate with this model.
Thank you, Tim. So I think we are we are at the end. If you can stop sharing your screen, I will just show to the participants the last thing that I want to see. We discussed today about TSO. How do they see the electricity system, or the decisions they have to take every day to keep it functioning and safe. If you want to know more, in the autumn, the Florence School organized an online course with Professor Meus and with some of my colleagues. It's on the evolution of electricity markets. But if you go on the website and look at the table of content of the course, you will see that several of the lectures will really address the interface between system operation and the electricity market. So all the concept, congestion management, balancing, system operation guidelines, you will find additional details. And so if you were attracted by the talk of today, or if due to your job you need to learn more about that, I really recommend you to look at all of this. Having said that, I would like to thank you, team. I would like to thank Daniela that support us from behind, and invite you to stay tuned to our website, and after the summer to join in other talks or webinars or whatever we will organize. Thank you very much. Thank you, team. See you next time.
Yeah, thank you very much. It has been a pleasure.
The pleasure was from us. Bye-bye.
Bye-bye.